I'm happy to be here today. As we said already, the talk is about from remote priority flow control towards source flow control. This is a team effort here at Intel. The team is J.K. Lee, me, Jeremiah Spledin, then Yanfang Lee, Gregor Zhericek, Ashutosh Agrawal, and Rong Pan. And I'm now going to explain what the difference is between remote priority flow control and source flow control, and what the context of the whole project is. Okay, by the way, can you see my mouse pointer before I continue?
Yeah.
Okay,
Yes.
perfect, thank you. So we are talking about incast congestion in data centers. This is the context of our work. So incast is a many-to-one traffic pattern where many senders send traffic to a single receiver, either by accident or on purpose. In both cases, this, of course, can lead to congestion. And this congestion usually happens as the last hop switch before the receiver. So the last top of rack switch usually. And the congestion can have a big impact on the tail latency of such traffic. And this in turn has a big impact on the performance of the application workload and the potential scale you can run an application at. And we are talking specifically here about incast in the context of remote direct memory access workloads, so RDMA workloads. And here the state of the art is something like RoCE v2 with DCQCN. These are just two protocols. I don't think we have to go into detail here that are used today. And RDMA workloads become more and more widespread in data centers, specifically for very high performance applications like HPN or AI training. And one of the things here that make incast more harder to manage is the fact that many of these protocols start sending at line rate, which means once an incast is in process, it's requires really quick reaction time. So the assumption here is that if we want to do anything about the congestion buildup or the congestion or prevent the congestion, we'll have to react in a sub round trip time. And round trip time here means the time in a congestion-free network, the minimum congestion-free round trip time, NIC to NIC. So this is really what we also call the base round trip time, the really lowest round trip time you can look at. So we have to be very fast. And what are the potential solutions that exist today? Of course, the go-to approach usually in this kind of setting is the end-to-end congestion control. Many of these protocols have those built in, such as DCQCN, as I mentioned before. And they usually work by detect congestion on the end-to-end path. For example, the data packets will carry a congestion notification bit. And if it experiences congestion, it will notify the receiver, and the receiver then will signal back that the sender should slow down. However, because the protocols are designed carefully to not overreact, what happens is that, for example, the sender could cut the rate by half on the reception of such a congestion notification. But that would mean that it will take many of these congestion notifications and many RTTs in turn to actually get to a sending rate that's sustainable for incast. Which kind of makes sense because, of course, the protocols were not designed for incast in the first place, right? That was not the original idea. But that means that we have RTTs in the hundreds of microseconds up to milliseconds. And now compare this to the congestion-free base RTT that you can expect to be in the range of single-digit or double-digit microseconds. So this is an order of magnitude higher. So clearly this doesn't really help us for incast events. Now, what else do we have in our toolbox today? That's hop-by-hop layer 2 flow control. The most widespread system is IEEE 802.1 QBB PFC, or priority flow control. Here the idea is to have a very low latency mechanism that allows a network device to pause the traffic on a specific queue or priority, as the design calls it, basically to stop sending on this priority. So the initial idea was to have a lossless Ethernet. That's the background of PFC. And what happens is if the buffers grow too much and there's the danger that a drop level is going to be reached at some point in time, the switch will then tell its neighbors to stop sending. And this is a very neat approach. However, it has, especially at scale, some side effects that are really hard to manage on the operational level. And I will explain a little bit in detail what can happen here on the next slide. So in PFC, we have here a small depiction. We can see these small server boxes on the left and the right side, and we have these gray or these white boxes, which are the switches in our network. And if we look at the purple lines, we can see we have a 3-to-1 incast here, which leads to congestion. And if the congestion grows too much, then PFC kicks in and this switch will tell its upstream switches to stop sending traffic. And that is effective at stopping, preventing packet loss. However, what can happen is if the senders don't stop immediately, and it's the senders over here, that now, of course, the congestion can spread because now the buffers of these switches continue to grow. And over time, they also can, in turn, spread the signals upstream. So you have the spreading of the PFC signal, and that can lead to situations where, for example, now this blue flow over here is affected by the congestion event over here, which is completely unrelated, right? So we can have this head-of-line blocking phenomenon, in addition to the fact that we now start to use the buffers all over the network. And there are even some implementations where this PFC spreading can cause deadlocks, so which completely locks up the network on this specific priority. So this overall means that PFC is really, really hard to use in practice, especially at scale, and it's probably not a good candidate to solve our incast issues that we try to solve here. So we concluded that we need a new layer 3 flow control mechanism to address this problem. And the basic idea is actually very simple. So at the congested switch, we detect the queue build-up early. We compute the minimal time we need to get from the congested queue to a acceptable queue depth. And then we basically send this pause time back towards the incast senders. And we do that immediately from the switch. We don't wait for the packet to arrive at the receiver, but we do it immediately from the switch to do the whole thing as quickly as possible. And now we have two flavors, as mentioned in the title of this talk. There's remote PFC and source flow control. The first approach that we can take is that we send the packet back to the sender of the traffic, but the sender side first stop switch in the network, the top of rack switch, the TOR switch, intercepts the packets and converts it to a standard PFC frame. The same PFC mechanism that we explained before, but now it's only used between the switch and the sender NIC. And the nice about this approach is that we can use today's NICs because they all understand PFC, and it's a very low latency mechanism. And this flavor of our design is what we call remote PFC, or in some cases also source PFC. But in this talk, I will stick to remote PFC. And another more outlooking approach is what we can also do is we can send this message directly to the sender NIC. And then the NIC itself just specifically pauses the flow that causes the congestion. Instead of pausing the whole priority as a remote PFC does, we just pause the flow. And we explain later a bit what the differences are here. Now, back to our network view. How does remote PFC work? Again, we have our 3-to-1 incast here in the purple lines. And we have congestion here on the link towards our receiver. Now what happens is that the switch will detect the congestion early and will immediately send back a notification to the sender of the traffic. The Tor switch will intercept this message and will convert it to a PFC frame. And the PFC frame will stop the traffic in a very short amount of time on the sender NIC level. And that, of course, means that the whole issue of head of line blocking in the network, in the network is completely solved, right? We don't have any head of line blocking anymore in the switches, which is a great advantage, and of course solves all these operational headaches we have with PFC, but you have to be very careful, and we don't have this anymore, right? So we now have removed this whole issue from the equation. And at the same time, we are very quick because we send the notification directly from the switch. It has also the advantage that we can use today's state-of-the-art RDMA NICs. The only small downside, and this is depicted here, is that in the blue line, we can still have a little chance of still having head of line blocking, because if there's traffic that's meant to go out from this server to somewhere else on the same priority, we can also experience head of line blocking because we are blocking the whole priority here and not just a single flow. So this is the small price we have to pay here. And if we now move on and compare this to source flow control, again, the same image, but now what happens is we pause the sending flow directly. So there's no PFC involved anymore, and that means we get completely rid of any chance of having head of line blocking or interfering with traffic that's not directly involved here. And that's of course the goal. That's the goal we are working towards. The only small difference here is that we require next generation RDMA NICs. So this is not something we can deploy today. And that's also the reason why in this talk we will focus on remote priority flow control or remote PFC, because that's something that you can deploy today. And we actually implemented remote PFC on Intel Tofino 2 switches in our lab. And we can now share a little bit a closer look on how this works on the end-to-end view and zoom a little bit closer to the switches and the evolved devices. So again, we have a small depiction here of how the network looks like. We have two senders. We have a top-of-rack switch at the source. We have a receiver, and we have a top-of-rack switch at the destination or receiver. And we have a 2-to-1 incast. And now at the switch level, we detect the incast buildup at the ingress. And that's basically in the packet before it goes to the queue. And this is important, as we'll explain later, because we detect incast before the packet experiences queuing, and that makes us really fast in terms of reaction time. Now we have this incast traffic, we detect the congestion, we immediately send back a layer 3 signaling packet. It bypasses or travels to the aggregation and core switches without causing any side effects. It arrives at the source Tor switch, where it then is converted to a PFC frame over here, which is able to stop the senders of the specific priority in a very short amount of time. And of course, at the same time, the end-to-end congestion signaling still happens, but as depicted here, because these packets that carry the congestion information are also part of they're in the congestion queue, which means they themselves experience congestion, which means they can arrive at the receiver, which is with a significant delay. And only after receiving this information, the receiver then will generate a congestion report, which will then be sent to the center, which could, in this case, even be after the whole remote PFC mechanism has triggered the pause already. So the key feature really of remote PFC is, first of all, getting rid of the side effects of PFC, but keeping the low latency and making sure that we can react to these congestion events in a sub-round-trip time frame. And again, round-trip time here means the congestion-free base RTT. Now, at the same time, We are not trying to completely replace PFC, so we cannot provide a guarantee that we won't drop packets. However, the system is designed in a way that it keeps the buffer utilization low at all times. We get rid of the PFC side effects. And the nice thing here is that, as I mentioned before, it doesn't require any changes on the NIC side or in the core network. The only thing is we need to support the remote PFC on the top of rack switch level. For example, using a Tofino 2 switch. So this is the end-to-end view. And now if we zoom a little bit more deeper on the programmability side, so how the switch looks on the inside, this is a abstract view or a view on the Tofino switch. You can see here the packet comes in on the left, it goes to the right. And this is the processing that happens inside of a Tofino switch. So we have an ingress pipeline where the packet is processed before it goes into the queuing system. And then there's a pipeline that's applied after the packet has been dequeued and sent out to a specific port. And both of these pipelines, because it's a Tofino switch, they are both programmable. And in this case, it's a Tofino 2 switch, and this means we have this neat feature where we get congestion status reports from the queuing system into the programmable ingress pipeline. And this means that we can detect the congestion early if we see the packet goes to a congested queue. We still, of course, enqueue the packet, even though it's congested, but it's still better than packet loss. But what we also do is we create a signaling packet, and we enqueue that signaling packet into a high priority queue down here that is not congestion. And this means that for this signaling packet, we can bypass the congestion and make sure that we get a reliably low delay when sending out this signaling packet back to the sender. And that actually allows us to have this extremely low latency when signaling the pause back to the sender. And in order to make sure that this high priority queue utilization stays low, we have a system in place that makes sure that for every sender, we only send a report in a specific time interval. So we have a suppression system in place that ensures that we don't send out too many packets at one point in time. Okay, now we implement that system, as I mentioned before, and we ran it in our testbed to see what the effects are and if it actually works as we intended to work. This is our demo testbed. You cannot see up here we have two top-of-rack switches, which are, sorry for that, which are directly connected, top-of-rack switch 1 and 2. And we have a total of 8 servers that are connected. And these 8 servers handle 2 separate incast events at the same time. So we have a 4-to-1 incast between sender 1 and receiver 1. Receiver 1 receives at 25G and sender 1 sends at 100 gigabits per second. And then we have a large incast event of a 20-to-1 incast in blue, that's receiver 2. And the expectation here is, because it's a large-scale incast, there will be significant queue buildup on top of rack switch 2, which at some point in time will trigger PFC, and then PFC will actually tell the upstream port, in this case top of rack switch 1, to pause sending traffic. And this will cause head-of-line blocking caused by the blue traffic for the red traffic. So the red traffic will suffer from the blue traffic. And we will want to show that SFC can help us here. And what we did is we actually collected the actual queue depth utilization on the switches using the device telemetry feature of our Tofino switches and 3 different ports. The main port we are interested in, of course, is the link between TOR 1 and TOR 2. But we also collect data from the links that go from TOR 2 to the both receivers. The red one, receiver 1, and the blue one, receiver 2. And the key result for us is, of course, that if we look at the TOR 1 to TOR 2 link, the gray one here, if you look at the horizontal axis, that's the timeline over the throughout the whole experiment. And on the vertical axis, that's the buffer utilization. And on the top, you have the PFC results, and on the bottom, you have the remote PFC results. And you can see that with PFC, you have a very high buffer utilization, and that's, of course, because of two reasons. First of all, it will only stop senders if the buffer is pretty much full, and there's a danger of packet drop, both on Tor1 and Tor2 and Tor1. And the other, of course, is that it will actually stop the traffic between Tor1 and Tor2, because it works on a hop-by-hop basis. But we can see here remote PFC, because it goes directly back to the senders from the receiver. It will never actually shut down this link. And thereby we get a much, much reduced queue utilization without actually impacting the performance negatively. And we can see here actually the effect also works for the receiver ports, because we early in the process in the queue build-up, we tell the senders to stop. But we never get a significant queue build-up here, which is also very nice to see. But that's the key effect, and we can show here that the system works as intended. We also took a look at the effect on the flow completion time, which is from the application level, the key metric that we are interested in. It tells us how long it actually takes the network, the work to complete the whole workload. And on the horizontal axis, we can see the flow completion time. And on the vertical axis, we can see the CDF. And for the median, we can see that we can get a flow completion time reduction of about close to 75%, in this case 73.3, from around 15 seconds to around 5 seconds. That is a great result. And for the 99.99 percentile, we still get an 8% reduction of the overall flow completion time. And that's a very nice result in terms of application performance. Okay, now concluding our introduction of remote PFC is that we have shown that remote PFC can actually help to reduce the buffer utilization and flatten the curve for incast workloads and data centers. We are using the programmability features of Trofimo 2 and 3 for sub-RTT edge-to-edge congestion signaling. And the remote PFC design is specifically compatible with standard NICs that exist today that support PFC. And for the future, we are working on the standardization of PFC at IEEE and IETF. So we are really looking forward to that. And there's a plan to upstream the PFC, the remote PFC feature to the standard switch abstraction interface, from OCP, which is a standard interface for managing switches, which will help us to get a wider adoption of the system. And of course, we are working on source flow control together with next generation RDMA NICs to get completely rid of head-of-line blocking in this context. Yeah, and with that, I thank you for your attention and interest, and I'm happy to answer questions.
Okay, thanks, everyone. So now I think we have 3 minutes for question. So,
Hey, Jeremiah, this is Chen from as a great work as station. But I still have a question. That's the first one is look at your graph. It seems that you identify.
I'm sorry, I really have a hard time hearing you. Can we improve the quality a bit? I don't know, maybe get the microphone a bit closer. I'm sorry for that, but
it's okay.
Jeremiah, it's great work.
hi.
I have 2 questions about this. From your graph, since you identify which gas will impose pressure and push it back. Right? I don't see you push back all the gas. You do that?
I'm sorry, I didn't.
Okay.
The voice is interrupted. I really have a hard time.
Really? Okay. My question is, look at your graph, right? You seem that you identify which incas post congestion, so you push it back, right?
So the question is if we identify the individual contribution to the incast.
Right.
We actually don't do that. We just check if there's a packet arriving on the congested queue from a specific sender.
Okay.
We don't actually track how big the contribution to the incast is.
Because for your view graph, we only have one incas get in far. And second question is, how long is stop sending? So it's a way until this end-to-end congestion get in. How long?
Sorry?
How long you stop this new car to send a car? I mean, you might understand my
Yeah,
question?
how long? I got how long, but then the second part got lost somehow. I'm really sorry for that, but the voice quality is kind of, it's really hard to hear from you.
Okay. My question.
Now it's much better. Yeah.
My question is, you ask the sender to stop sending traffic for how
Yes.
long?
So we calculate so we look at the current queue depth, and we have in our configuration a target queue depth that we deem acceptable. And then we calculate the time it will take, or the time the sender needs to pause to get there. So the assumption is, if at this point in time we'll stop all senders at the same time, how long does the pause need to be to actually get to an acceptable queue depth? And then we take this information and spread it. And although there's, of course, a signaling delay in the overall system, we still get to an acceptable level by using this approach. It's very simple, but it's very effective.
Yeah, but the DMC has this, so you carry that time information back to the center?
Yes. And basically, it's the pause duration. It's not the absolute time. It's the pause duration.
Pause duration. So you calculate at default switch.
Yes, at the switch that sends out the SFC signaling frame, this switch will calculate the overall pause time in microseconds, and it will just send it back to the sender.
Okay.
And then in the pause switch, it converts to the PFC time.
And also my third question is, you actually doesn't identify who actually caused that congestion, right? So you actually send it back to everybody to stop, right? So how
Yes.
about that's like a advert flow which caused the congestion, but you stop rest of them to avoid the congestion?
The idea here is, I hope I got your question right. So we send it to everybody, yes. So if there's a packet arriving in the congestion queue, we tell the specific sender to stop. But since we do this for every sender, but we only do it we only pause it long enough to actually get to the acceptable queue depth, there's actually no loss in throughput, right? So this actually, we are just removing the congestion from the network. We are not losing throughput. That's the overall idea. And thereby, even though we can pause sometimes some senders which didn't contribute very much, statistically, in the end, we still get to a good result because the sender will send its packet later, but the queue doesn't run dry in the meantime, so we actually don't lose any throughput, and the overall end-to-end performance is still good.
Yeah. What
This
it
makes
means
sense.
is some of flow will get penalized because they go along with and
So, okay, so your question is about fairness?
what?
If your question is about
Question
fairness?
because of that, then some of like flow will get penalized because of there's a one advent flow to go along with same people.
Yes, so that's actually, so if it's, for example, if you have the extreme case that you have a sender that sends a single packet to that congested queue, and tries to send out tries to send out lots of traffic to a different host, this can actually still cause head-of-line blocking.
Okay.
So this is
Okay.
actually an issue, yeah, and that we are investigating, and this is what we are trying to alleviate with the source flow control, with the SFC, because there we can get rid of it completely.
Okay. Thank you, Jeremiah.
Thank you. Very interesting questions.
We have one more question here. Can you come forward?
Okay.
Yeah, I have one question. Actually, last slide you were talking about only supporting remote PFC at 2 and 3. And my question is, since
This slide?
programmable,
Slide.
which Tofino is actually programmable, why is not Tofino 1 at the current node?
Sorry, I think
Jeremiah,
there's
can
something.
you hear the question?
It really had a hard time hearing the question. I don't know. It seems something is wrong with the microphone or so. If you get closer to the screen, it seems to work better. I'm sorry for that.
You
Can you
mentioned
repeat the question?
the leverage of programmability of the Tofino 2 and Tofino 3 right here, right?
Mhm.
So how
Yes.
about if we can use the Tofino 1 to achieve the same goal, to see the same?
Okay. Yeah. So you can do the same thing on Tofino 1. The key difference is, the key difference is that on Tofino 1, this feature doesn't exist where we get this QDepth information directly from the TM. So in order to get this on Tofino 1, actually we prototyped this. So our colleague Yanfang Li actually did this. What you can do is, instead of using this built-in feature in Tofino 1 in Tofino 2, in Tofino 1 you can recirculate a packet with the same information, right? So what you would need to do is you would dequeue a packet, you would see the QDepth, and then you would recirculate the packet, sending it back, and then distributing it throughout the switch and updating the ingress pipelines. You can do this, and at a certain scale this might work. So if you're doing it for research, this might actually be a thing that can work out. However, at a production network, you wouldn't want to do it because the recirculation packets can, well, if you have a fully loaded switch, this is a problem, right? You basically need extra bandwidth for that. And usually in a production system, you don't want that, which is why we have the system in place. But for research applications, you could still try to do it with the recirculation of a packet. Does that make sense?
Why the different one two lines?
Is this the one the Tofino 1 can get the QoS and the egress part? Am I correct?
So the difference is that there's a specific hardware block in Tofino 2 that's new, right? This hardware block does nothing else but providing information from the QDepth information directly from the queuing system to ingress pipe. It's a specific hardware that's not exist in Tofino 1. In Tofino 1, you can only achieve the same thing by basically recirculating a packet.
Yeah, we know that. Yeah, thank you very much.
Okay, yeah, thank you. Very interesting question.
Remote PFC only exists in Tofino, not in some kind of dating program.
Did I get the question right? It's about the question, is remote PFC only doable in Tofino?
Yeah, is that comparatory to Intel Tofino?
It's not necessarily. So as I said earlier, we are working with IEEE to get this standardized. So in the future, we are seeing other devices or other switches to pick this feature up as well. However, because Tofino is programmable, we can do it today, right? We don't have to wait for new silicon. We can just do it. And that's actually what we did for this experiment.
Okay. Any question, comments? I think it's also about the time to conclude this session. So let's thank Jeremiah Blindin again from Germany. Are you in Germany right now?
No, I'm actually in the US. I'm in Seattle.
Okay. Thank you for your time for sharing the topic with us. Thank you, Jeremiah. Thank you.
Yeah, thank you for the questions and thank you for having me.